So let's quickly talk about what it means for a variable to be another or independent predictor of the outcome. So sometimes these get referred to as being risk factors. What these are is they're variables that independently predict the outcome or y, but they're not confounders, mediators, collinear variables, effect modifiers. So the kind of classic diagram looks like this. Right? What effect does x1 have on the outcome? That's our question of interest. And this variable x2 is also associated with the outcome. Okay, it can predict the outcome, but it is not associated with x1. It's not on the pathway between, not associated with x1 in any way. Okay, so it's another predictor of the outcome variable. Let's talk about the criteria for these. Well, I guess before we get into the criteria, let me just quickly say here that when building an effect size model, we may choose to include these variables, or we might choose to exclude them. Okay, the argument for including them is that quite often if x2 is a good predictor of the outcome, right, if it's pretty associated with the outcome, what including it tends to do is decrease the standard error of B1. Right, this here. Now think about it this way. If this is really good at explaining the outcome, we're going to get more certainty in the effect that x1 has on the outcome. Right? Again, if this explains a lot of y, explains a lot of the outcome, then we're going to be more certain or more precise in our estimate of what effect x1 has on y. So that's the argument for including it, is that it tends to be another predictor of the outcome and it increases precision of the estimate of our variable of interest. And just a reminder to think about what this does. Decreasing this standard error is going to narrow the confidence interval around B1. Right? It's going to give us a more precise estimate of the effect of x1 on y. Arguments for not including independent predictors are, if it's not a confounder, we don't need to adjust for it. Right? This coefficient B1 is not really going to change much whether x2 is included or excluded in the model. So there's arguments for both. Where I usually tend to fall on this is that if it's quite a good, like strong predictor of the outcome, or a very recognizable predictor of the outcome in literature, I'd lean towards including it in the model. If it's a pretty weak predictor, or it's not been identified as a predictor in literature, if we have lots of other variables in our model, then I'd probably lean towards excluding it. So some of the criteria for identifying these. Our usual one, makes sense. Makes sense conceptually. So it makes sense that x2 is associated with the outcome, and it makes sense that it should not be associated with x1. X2 is associated with the outcome. We can think that makes sense conceptually, and we can check numerically. X1 is not associated with x2. So there's no link between these two variables. And what we're going to tend to see is when we include it, so this is just numerically what happens, when we adjust, we really shouldn't say adjust, because if we're not, it's not a confounder, we're not actually adjusting for it, but that's one of the words I've been using. So when we adjust or when we include this variable in the model, there's no change in B1. Right, again, if these are not associated, B1 should not really change much. So there's not really much change in B1. But the standard error for B1 decreases. Right, and again, we said that conceptually, if x2 is a good predictor of the outcome, right, we're going to get more precise estimate of the effect of x1 on the outcome. So this is just the idea of independent predictors, or what are sometimes called risk factors. We talked about the arguments for including them, and we talked about the arguments for excluding them. And I personally think I take it on a case-by-case basis.
Stick around, guys. There's more to see, and please stay safe.